Alright, so we can define linear speed in a circular motion with the formula V equals S divided by T. So V is linear speed. S, if we have something going in a circular motion, like you can think about the story of, say, like David and Goliath, or any story where someone has taken and twirled something around, like a rock in the end of a sling. That would be traveling in circular motion. Maybe not perfect circular motion, but in circular motion. And so, if we looked at a certain time, like say when time equals 0 to time equals 3 seconds, then that rock or that whatever is in a circular motion will be in two different places, from 1 second to the next, or from no seconds to 3 seconds, or something like that. And so the S here, that's arc length. That will be the arc length from one time to another time, divided by T, the time that it actually took to do that. And that would give you linear speed in a circular motion. But that's not really much difference than if you were to figure out the linear speed if you were driving down the road. It's not that different. So what does circular motion, what does that bring into everything? Well, remember we have this angle measure here now that we can form between the two radii. And so that would be like our theta there. And that's our S. Of course, that's the R, the radius of the circle. And so we could also, if we're going in circular motion, look at the angular speed. And the angular speed would be the speed that the angle is traveling. And so the variable we use for angular speed is the Greek letter omega. It looks like our letter lowercase w. So omega, if I say omega, I'm really talking about this w here that I'm writing. But omega is equal to the angle measure that's been swept out divided by the time. Okay? Now, if I was to set S, remember arc length we said was the radius times the angle measure? If I was to do that in this first equation, then I was to set my two equations equal to T, and then set those two equal, I could solve and get another form for linear speed. And another, or an alternate formula for linear speed is V equals R, that's the radius, times omega, the angular speed. So you may be thinking, well, which formula do I use for linear speed? Well, that's going to depend on what information we have in the problem. Also, with angular speed, we want to put our answer in radians per unit of time. So our final answer for angular speed, you want the units of your answer to be radians, and then per unit of time that could be, you know, seconds, hours, minutes, whatever, a unit of time, days, okay? And so here's an example of angular speed. Angular speed can be used to describe the rate of that an engine turns, parts of an engine turn. So everyone in here, whether you know it or not, you've probably seen a RPM gauge on some type of vehicle or whatever. And we can actually take RPM, revolutions per minute, and change that over to radians per minute. So we can look at the angular speed in radians per unit of time. For example, if you were told that your car was going 900 revolutions per minute, I usually set the cruise on about 70, 72, and my RPM in my vehicle is about 2,000. That's usually where I sit. Okay. So let's say that we had 900 though. The way that we would want to write this angular speed, we wouldn't want to leave it 900 revolutions per minute. Okay. We could rewrite this by using a conversion, so that this will be radians per minute. So I want to multiply this times 2 pi, and that's radians per what? Revolution. Aren't there 2 pi radians in one revolution? Yes. So my angular speed would be 1800 pi radians per minute.